interaction of light with matter is one of the fascinating topics in physics and has also deep implication in understanding a variety of sciences and technology. This has been a research interest of mine for almost 2 decades now, and this has led me to look at concepts of both light and matter and their interaction in a systematic way. It is also interesting to tell you that when you consider light matter interaction, in some particular cases you will have to restore to classical physics, but in certain cases you will have to restore to quantum mechanical picture. So depending upon the situation, you would have to now look at light matter interaction either from a complete quantum mechanical interaction or semi-classical interaction, or in certain cases classical electromagnetic interaction. So this has been a topic of interest in my research group for now almost 16 to 17 years now. My research group is going to turn 16 years very soon. In fact, it's one of the very fascinating questions we have been interested in understanding how light interacts with matter. So this also has led us to a variety of research problems in this particular area. We have been looking at this problem from various different perspectives, from light scattering viewpoint, transfer of momentum from light to matter, including optical trapping, optical tweezing, rotation of objects, structured light, soft matter systems, and also in certain cases understanding molecular spectroscopy, including Raman spectroscopy, and understanding molecular light scattering in such kind of interactions. In the same line of research, there has been new developments in understanding this light matter interaction from a systematic perspective. And it is also important for us to really understand this concept in a slightly broader context, in the context of, let's say, optical momentum itself, which is something equally interesting. The motivation to give this particular lecture and also hopefully series of lectures is one of my recent research grants in ANRF. ANRF, as you know, is a research body which funds research. And this is also a government organization which interfaces with researchers to really come up with new ideas. And I have been awarded one of the grants recently in physics, which is it's called as optothermal binding of plasmonic matter. And that is a research topic which I and my research group are involved in. So the idea behind this particular research project is also to bring in optical momentum and thermodynamics on a single platform. It also has some very interesting implications of understanding light matter interaction from a perspective of statistical physics and statistical optics, and also includes some new developments in the way structured light has been utilized to understand light matter interaction. It also involves a lot of Brownian dynamics, and it brings in its own interesting viewpoint. And that is something I and my research group have been researching over the past few years or so. Now, within the framework of optical momentum and its interface with thermodynamics, the topic of optical momentum itself actually is very rich. In fact, so much so that it has had very deep interest and history in terms of understanding how light interacts with matter. And there is so much of kind of, developments which have happened over the past century or so, where you would see some fascinating aspects of light matter interaction, both in terms of the light and also in terms of the matter. So much so that you would be able to now understand what it takes for us to design materials and design matter to really go deep into this particular interaction. One of the aspects which we have been looking at in this context is also to understand how at all you would be able to utilize the structured light, for example, polarization and the wave vector and other kind of parameters can also be brought into to the Fourier. So it also has very deep applications because if one looks at this particular viewpoint, one can look at applications which can be something like optical tweezers, and spanners. And nowadays, you can also have something like light sails, which is a very futuristic project where people are interested in looking at what happens if you use optical momentum to push objects in the space environment. As you know, the drag in the in outer space actually is minimal because there is not many kind of currents which are available which would resist the movement. So you can use momentum of light to push objects in a systematic way. So the kind of lectures I am planning to give here is motivated towards some of the research what we have been doing. So this is slightly more at a research level, PhD level lectures, where I'm going to look at some questions of the field itself, try to kind of discuss some aspects which might be both quantum mechanical in nature, classical electrodynamics in nature, and in certain cases, for example, in optical binding, even quantum electrodynamics has to be brought into the picture. It has beautiful theoretical physics and a lot of experimental aspects connected to the theoretical physics. And combining them together also has some interesting developments in computational physics. In my research group, we try to kind of bring all these three things together. Although we are mainly an experimental physics group, but we are also deeply interested in theoretical analysis and computational physics of understanding this kind of interaction. So one of the crucial aspects of looking at this kind of interaction is to also to come up with authentic sources. We do write research papers. We also discuss a lot of research papers in my group, monographs, books, and also classic papers, which has very deep implication both in terms of historical relevance and also in certain cases philosophical relevance. So that is one of the motivations of these lectures which I intend to give going forward. And this kind of becomes a repository, hopefully for my own research group members who would be able to probably utilize this platform for them to relook at some of the basic concepts, fundamentals. And also I do enjoy, kind of teaching this aspect, which this is something which I've been learning for many years. And there's a lot to learn for me going forward. And also in order to execute this project, it would be necessary for me to develop these ideas in a systematic way. And hopefully this will be an interesting way to go about doing it. There is also a lot of interesting questions related to the optical momentum. As I told, one can utilize this optical momentum from various different perspectives. But one of the key aspects which we will look at is to also understand some questions related to light matter interaction from a very fundamental viewpoint. For example, there are interesting controversies, in some cases so-called paradoxes, although one has to be very careful while calling something as a paradox or something like that. But there are some interesting questions related to all these things, which I hopefully plan to cover as I proceed going forward. So the important aspect is to mention that a lot of stuff what I'm going to discuss would be mainly in the realm of research questions and also research problems, research papers, and also to a certain extent monographs and historical papers. I'm going to highlight some aspects. And I'm going to use, of course, my favorite platform of handwriting and also speaking to you directly, so that there will be some kind of an interaction going forward. Okay, with this background, let's get started with some particular, aspects. We're going to look at some questions related to the fundamental quantities. Let's look at some of the fundamentals. So the basic fundamental aspects is to acknowledge the fact that if you have electromagnetic radiation, which in this particular case light, it would actually carry some particular frequency. Let's say nu is the frequency. Then the energy of such a system is essentially given by E is equal to h nu. This particular system can also carry a momentum, and that particular momentum I would just call it as P, and this particular momentum can be now represented by the energy over C, where C is the velocity of light. This can also be expressed as Planck's constant h over the wavelength of the light, lambda. Furthermore, this can be expressed as h cross k, where k is the moment which we are interested in. So if you want to utilize vectorial projection, then you would represent this as P is equal to h cross k. Now the crucial aspect is for us to really look at this equation and try to understand it in detail, and what are the possibilities, etc. One of the aspects which you would already realize is that you would be able to now look at this such that you can write as the modulo of this particular vector to be equal to 2 pi by lambda. So this will be directly associated with whatever system you are now looking at. Now, one of the crucial parts I would want to emphasize that every photon essentially carries this kind of linear momentum, which is inversely proportional to the wavelength. Okay. This also has very interesting connection, because as the wave propagates through a medium, there would be changes in the refractive index, as you know, and therefore it can also cause some changes in the momentum. But that is something which we're going to take it up further as we move along. The second aspect is to just look at this whole thing from a classical ED viewpoint. So classical electrodynamics. So in the classical electrodynamics, if you associate the electromagnetic wave to carry a vector E and a magnetic field P, then there is something called as pointing vector. This pointing vector, which is usually represented by capital S, which I'm going to use that as the term, is now given by 1 over mu naught cross product of the electric and the magnetic fields. Okay, now this is an important vector which is going to be associated with the way the information also gets transferred, the way actually you can force an object, and it will play a critical role, as you will see going further in many of the discussions what we're going to have. Associated with this is also a momentum density, and this momentum density, which we're going to represent it as small g, is a vector, and that momentum density is capital S vector over c square. Furthermore, this particular g vector can now be represented as epsilon naught, the cross product of electric and the magnetic fields. So the momentum density tells you that how much of specific kind of momentum is there in is packed in that particular wave per unit area or per unit volume, more strictly speaking. And you will see that this actually has to be revisited in a systematic way. We will have to understand this carefully. Most of the time, for example, you read books like Griffiths or any conventional electrodynamics book, it loosely defines this term, but there's a huge implication of understanding this. And as we proceed, I'm going to build upon that concept carefully going forward. Okay. Now, one of the crucial parts which is associated with understanding electromagnetic momentum is derived from something called as Maxwell's stress tensor. This is a tensorial quantity, and that particular stress tensor usually is represented by this kind of double arrow on top of its head. And this Maxwell stress tensor is connected to the force which you can impart on a particular object due to the electromagnetic waves. And that particular force F is now given by, let me redraw this, is now given by F is equal to a surface integral, the Maxwell stress tensor, a dot product with this surface element ds. Of course, this also is a vectorial quantity. Strictly speaking, there is also another term, okay, which is minus rate of change of the field momentum. But many a times, this actually has a role which is equal to 0 if that particular field momentum does not change with respect to time. Because there's a rate of change of time, as you can see. So if there is this particular field doesn't change over an average time, you can take this particular quantity to be essentially 0. Okay. Now, this is also related to our well-known, Lorentz forces. And just for the sake of completeness, if you have a charge Q, and if you have this charge Q kind of put into an electromagnetic field which is represented by E and B fields, the force on that particular charge is essentially given by Q times the vector E plus the cross product of the velocity of that particular particle and the magnetic field. Okay, there are nuances, further definitions related to this, but it is just a working definition for us to take into consideration. Now, if you look at this whole perspective, this really brings in new questions. For example, how do you transfer momentum in such situations? What are the mechanisms through which you would be able to impart the momentum, etc. But before I really go into specifics, I want to give you a very interesting and overview concepts, which is very much part of our literature, which is an interesting controversy, which has been playing for multiple years now, almost more than a few decades, close to 70 to 80 years, which is something called as Minkowski versus Abraham momentum. Controversy. Now, interestingly, in both these momenta, which are given by Minkowski and Abraham, are supposed to be actually authentic and is applicable in their own sense. For example, Minkowski momentum actually is mainly called as a canonical momentum, whereas Abraham's momentum is usually called as a kinetic. Okay. Now, the canonical and the kinetic momenta has some interesting implication, because the canonical momentum Pm, which is usually the notation which we use in the literature, is given by n times h cross k naught being the light which we are using, and n happens to be the refractive index of the medium in which this particular wave is propagating. The refractive index plays a very critical role here, because what we are talking about is the momentum of the electromagnetic radiation inside a dielectric medium, and what we are representing here as n is essentially the refractive index of the dielectric medium. Taking the argument forward, the kinetic momentum is represented by Pa, and this is given by h cross k naught by n, where n is the refractive index. So there is a lot of interesting arguments between these two things. One is actually a canonical, and it has some implications in understanding light matter interaction, whereas Abraham momentum is associated with the transfer of energy, and therefore also it's called as kinetic. And in some of the future lectures, I'm going to bring more light into this controversy. There's a very, very interesting debate, and depending upon which part of the interaction you are looking at, you will have to associate each particular term accordingly. Okay. We will now look at some basic aspects related to the light matter interaction. One of the aspects which I would want to highlight is, let's say I will call this as number 4, is the fourth point, which are essentially the forces and the related optical manipulation capabilities. Okay. Now, one of the crucial aspects related to this kind of interaction for us to really understand is to define kind of forces the light can impart, mainly in slightly more macroscopic sense. And there are various different forces associated with this. For example, one of the crucial forces is something called a scattering force. And this scattering force is generally represented by F scat, is proportional to the capital S, which is the pointing vector, which I had already defined. And there is something called as gradient force. And this gradient force, which is again grad, is proportional to the gradient of the intensity of the light, what we use. There's also a third term, which is a recent addition, only in the last couple of decades or so, which has been added to this particular interaction, which is usually called as a spin curl force. Spin curl force, which is usually called as F spin, is proportional to the cross product of the gradient term with the spin angular momentum. Okay, and that spin angular momentum will be defined going forward, and it has some very interesting connotation. Please remember, this particular S spin is different from the pointing vector S, because the spin angular momentum itself has some interesting terms depending upon the electric field, the imaginary part, etc., etc. But I'm going to build that going forward. Before moving forward, I want to just mention that spin curl force is what I have been talking about. It has a very interesting nature, because it is a non-conservative force, which means that depending upon the way in which you have the interaction, the path dependency actually is present. So, which also means that it brings in some very interesting, avenues for understanding light matter interaction, more so from the point of view when you have electromagnetic radiation which actually is structured, meaning you can now use structured light, you can structure the laser beams and study the interactions. Now, associated with these kind of forces, and as you can guess, is also an important concept, which is the angular momentum. In the angular momentum, as you would have already preempted, there is a spin angular momentum, which is associated with plus or minus h cross, and this is a single photon. So always remember that a particular photon can carry an angular momentum either plus or minus h cross. This is a kind of a quantized quantity. Okay, and there is also an orbital angular momentum. And this particular momenta has some very interesting implication because it is associated with a phase which is related to this e to the I L phi, which further means that you would now actually have photons which actually carry an orbital angular momentum which is equal to L h cross, where L happens to have a very interesting kind of connotation. This L is usually also called as topological charge. Because this particular L can take values from minus L through 0 to plus L, and therefore depending upon the value of the L, you would be able to encode information. And that is one of the very interesting aspects of the angular momentum, because you can now do information processing using angular momentum of light. And of course, you can also do information processing using linear momentum of light. But this is a new kind of prospect, and a lot of people have been already using. It's also used in some of the aspects related to the internet, and that is something I'm going to highlight as we go further. Because without the understanding of the momentum, you would not be able to appreciate these things. Now, one of the aspects which is also equally interesting, which is for me to highlight the fact that you would be able to utilize it also to study light matter interaction under microscope. One of the techniques which we have developed in our lab, and this is again thanks to many developments across the world, but we have been working on this particular topic for several years, and that is called as Fourier plane imaging. This is also called as momentum space imaging, and it's also called as back focal plane imaging. In fact, it's a very fascinating topic because it also utilizes optical Fourier transform. Because if you look at the electric field in the back focal plane of the lens, what is used to image the object, this actually can now be taken as the E sample, and essentially you have the X and Y plane, and then you take the Fourier transform of that. So I'm writing into e to the minus I kx x plus ky y times dx dy. Okay. So what happens is that you would be able to now take something in the real space and project it into the momentum space. And this is a very fascinating imaging technique. And what is the interesting aspect? You would now be able to utilize the angular spread of the light on the camera plane, which we essentially image the back focal plane of the lens, such that the angular spread, which is the azimuthal angle and the polar angles, in such a way that you now have the kx is now given by k naught n, if you are essentially using the refractive index of the specific medium, cos phi, and ky is equal to k naught n sin theta sin phi. So you now be able to now take sum of squares, and you would be able to get something out of it. The kz can also be defined, which would be able to project that in the cos theta term, so to speak. And the most important element what you are seeing is that there is a relationship between the thetas and phis with the momentum. So depending upon how the light is distributed in these angles, so essentially it is a plane, and you would have essentially a circle, and in that particular circle you would be able to image something. And if you image something in that particular circle, you now have a theta element and a phi element, right? It's an azimuthal angle and a plane and a polar angle. Depending upon the projection, you would be able to image the momentum of the light. And the momentum is directly encoded in the angles, and therefore it's called as Fourier plane imaging or momentum space imaging, so to speak. This is a very fascinating concept, and this is also related to some of the things what I'm going to do in our project. And we also will try to bring some new kind of perspectives in understanding this Fourier plane imaging and some thermodynamics and other elements going forward. That is one of the goals of that particular point of view. Now, you can also image evanescent waves, and you can also do isofrequency imaging, etc. There is many applications, and it has been extensively used in plasmonics. We have studied nanowires. We have studied Raman scattering in such kind of momentum space imaging. And there are plenty of applications, but the hope is also to give you an overview and the systematic physics behind all these things in greater detail. And I'm going to derive a lot of stuff related to these kind of interactions. Finally, before I wind up, I would want to actually tell another very fascinating application, which is the so-called dynamic light scattering. In dynamic light scattering, one of the crucial elements is that you also have a wave vector, which is generally called as Q. They don't use K most of the time because it depends on which particular sub area you are working on. So if you now have something called as scattering vector, this is generally represented by the scattering vector Ks minus the incident vector I, and the difference is usually called as the Q vector. Okay, and this particular Q vector essentially represents the momentum transfer. And if you happen to have an interaction where the Ks is equal is of the same wavelength as the Ki, then you do not have any inelastic element, and more so it is usually called as an elastic scattering. The magnitude Q in such a situation is usually given by 4 pi n over lambda sine theta by 2. And this particular magnitude, again, if you can see the interaction of the light, which is essentially coming from this particular subtraction, and this is associated with the angle theta. And there's a very interesting connection between the interaction vector and the angle at which the scattering happens. So which means that you would be able to utilize this also to study some dynamics. And how is that so? This is mainly coming from the fact that you would be able to use something called as autocorrelation functions, which is defined as G2 of tau. This is tau, and that is equal to 1 plus some particular term, let's say beta or something, where e to the minus let's say 2 times gamma over maybe tau is how you define this G2 term. And the important aspect is that this particular quantity, what I am defining as the gamma, has an interesting connection such that the gamma is now given by capital D times Q square. And this D happens to be the diffusion coefficient, which is so important in understanding the dynamics. So you can see that the D is essentially given by kBt over 6 pi eta r, where r is the radius of that particular particle, etc., etc. So the dynamic light scattering actually has a very interesting connection to the wave vector, and the wave vector essentially is now given by the subtraction between the scattering vector and the incident vector. And I'm going to also tell you how momentum transfer happens in such kind of situations. So to recap, what we have now seen is just some specific aspects of fundamentals. We also just kind of looked into the classical electrodynamic interactions. The third one was this the momentum in dielectrics, And the fourth point, what we also just looked at, is the angular momentum. And the fifth point was the Fourier plane imaging. And the sixth aspect is the dynamic light scattering. So what I'm going to go and actually expand on is some of the fundamentals in all these implications. I would also pay attention to the specific aspects of how the momentum transfer happens. For example, one of the crucial aspects which I'm going to highlight going forward is something called as optical binding. And optical binding is a very fascinating area of research where you can bring objects together, where there can be optically induced interaction between the objects which are brought into the potential well created by the laser. So it's an optically induced interaction. So you now have a laser light, you bring objects into this particular potential, these particles start interacting with each other, and they can actually go into a bound state, or they can also go into a repulsive kind of state. And that is a very fascinating concept, and is very closely tied to the momentum transfer and other concepts. The whole idea is to actually bring them together, and also some elements of statistical optics. These are the topics which we're going to build going forward, and I'm hoping that it will be useful, especially for research students, and maybe also even for senior undergraduates and anybody who is interested in this. And let's hope we will take up optical momentum and transfer that as efficiently as possible to everybody. See you next time.